Hi everyone. This last node of Unit 4 focuses on DeMorgan's laws. And we're going to very quickly go back over the NAND and NOR logic gates. And then we're going to take a closer look at each of those gates in terms of the DeMorgan's law for NAND simplification and the DeMorgan's law for NOR simplification. After that, we'll do a quick Boolean algebra theorems review from Unit 3. And then we'll go through a simplification example using those theorems in our new NAND and NOR simplification laws. So, to get started, let's review the truth tables for our NAND and NOR gates. We see the symbols here along with the Boolean expression notations. The truth table for our NAND gate, remember that if all the inputs are a 1, we get a 0 out. But if any input is a 0, we get a 1 out. And for our NOR gate, if all the inputs are a 0, we'll get a 1 out. But if any input is a 1, we get a 0 out. Now, remember when I told you in the last node that it is very important that the inversion bar be over the entire product for a NAND gate and over the entire product for a NOR gate? Well, the reason for that is that A and B NANDed together is not the same as not A ANDed with not B. Similarly, A and B NORed together is not the same as not A ORed with not B. DeMorgan's theorems actually have those, show us that those are actually opposite. So again, make sure that when you're NANDing and NORing that the inversion bar is over the entire product for the NAND gate or over the entire sum for the NOR gate. So here we have our DeMorgan's law for NAND gates. And again, AB NANDed together is not equal to A naught ANDed with B naught, but rather AB NANDed together is equal to A naught ORed with B naught. Our NAND is equivalent to a negative OR. And we can see that looking at the truth table here. Our NAND outputs are right here, as we learned them in the last node for our NAND gate. All 1s gives us a 0, anything's a 0, and we get a 1. However, if we invert each of our inputs, x naught and y naught, and OR them together, we'd have 1 ORed with 1, and we get a 1. 1 ORed with 0, and we get a 1. 0 ORed with 1, and we get a 1. So we see that our NANDed combination is the same as the ORed combination of the inverted inputs. Similarly, for our NOR gates, DeMorgan's law tells us that A NORed with B is not equal to A naught ORed with B naught, but rather A NORed with B is equal to A naught ANDed with B naught. So we have, same thing here, our NOR is equivalent to a negative AND. And again, in our truth table, we have the first column here represents our NOR output, just as we learned it in the last node. But we see if we invert our inputs and AND them together, we get an equivalent relationship. And also remember that for Boolean simplification, not our inverter has first priority, second priority is our AND multiplication, and third priority is OR. But just like with our mathematics, parentheses, our grouping symbols have to be addressed first, and that's why we have our NAND and NOR gate simplification laws, is so that we can get rid of that inversion bar over the entire product for a NAND or over the entire sum for a NOR, and it will allow us to then further simplify our expressions. As we make our Boolean functions more simple, the circuit necessary to implement that circuit becomes smaller, less expensive, consumes less power, and will operate faster. So before we do our simplification example, let's quickly run through the Boolean algebra laws. We went over these in Unit 3, and you can prove them to yourself with the truth table. Some of these were also proven in that unit. Remember that for Boolean algebra, our operations AND, which is indicated by multiplication, and OR, which is indicated by addition, are commutative, meaning we can OR things in any order or AND input variables in any order. And they are also associative, meaning that grouping doesn't matter. Commutative means order doesn't matter. Associative means grouping doesn't matter for or and operations. Recall that we also have distributive laws. If we distribute the a through the sum of b plus c, we end up with ab plus ac. And that also works for all the way up to FOILing out to binomials. A times c plus a times d plus b times c plus b times d. But the distributive laws also still apply in our Boolean algebra simplification. Some of the other laws, we have a double complement law that says if we invert something twice, we end up back where we started. We have the null law in the and form, meaning if we and something with 0, we'll get a 0. We knew that from our truth table. And if you get stuck on any of these, always remember to go back to your basic truth tables because they will help clarify things. But the and form of the null law should be fairly intuitive because anding with 0 is 0 and multiplying with 0 is 0. We have the or form of the identity law. If we or something with 0, nothing changes, which should also be intuitive. If we add 0 to something, nothing changes. So we have the or form identity. In the and form, if we and something with 1, nothing changes. Well, if we multiply by 1 in our arithmetic, we also know that it's analogous, so that one should be fairly straightforward. The or form of the null law may not be intuitive, but for this one, again, remember your or truth table. If we or something with a 1, we're going to get a 1. So if we or an input variable, no matter how many other inputs are on that OR gate, if we or it with if there's a 1, we're going to end up with a 1 out. So if you or something with 1, the result is a 1. And then our last set of laws may or may not be intuitive, but again, your truth tables will help you through. And if you need to, go back to Unit 3 and review the laws and the logic gates and the discussion there. The or form of the independent law says that if we or something with itself, nothing changes. If our input is a 0 and we have two zeros going into an OR gate, that's our OR unique state. We get a 0 out. If our input is a 1 and we tie the inputs together and OR two 1s, anything's a 1, we get a 1 out. So ORing a variable with itself will result in no change. ANDing a variable with itself will result in no change. Remember 0, 0, anything's a 0 into an AND gate, we get a 0 out. And 1, 1 is our unique state, which gives us a 1 out. So ANDing with itself is the original input bit. So ORing two input variables makes one of them redundant and unnecessary. ANDing two of the same input variables also makes one redundant and one won't apply. The inverse form says if we OR something with its opposite, well, if we OR something with its opposite, we know at least one of the inputs will be a 1, which means we'll get a 1 out. So again, your truth tables will tell the tale on this one. For the AND situation, if we AND something with its opposite, at least one of the inputs will be a 0, so we know we're going to get a 0 out. And then the last two are the absorption laws. A ANDed with the quantity A plus B will just give us A, and A ORed with the quantity AB, or the ANDed product AB, will also give us just A. So take your time and review some of these, and then we should go through a simplification example that uses some of these and also our new DeMorgan's theorems. Okay. To start, for our example, we're going to simplify the NORD combination of AB plus AC, ORed with A naught and B naught and C. Doesn't look too bad, but we will get to use our DeMorgan's theorems if we want to simplify this. So we're going to start just like with our order of operations for mathematics, grouping symbols, which this inversion bar, this NORD combination, counts as a grouping symbol, we need to break that up to get on with our simplification. So I'm going to apply DeMorgan's NOR theorem, or NOR law, to break that. And way to remember that is for DeMorgan's is break the line and change the sign. So if we use DeMorgan's, our AB NORed with AC will then become AB ANDed, or the NANDed combination of AB ANDed with the NANDed combination of AC. We broke the line and we changed the sign, or the operation. Okay? Now, we noticed when we did that, we got rid of that bar over that NORD combination, but we ended up with two NANDed combinations. So we're going to have to repeat the process to get rid of the NANDed combination. So we're going to apply DeMorgan's again for the NANDed combination of A and B, and also for the NANDed combination of AC. And again, if I break the line on the NANDed combination of AB and change the sign, or change the operation, I get A naught plus B naught. Similarly, if I break the line on the NANDed combination of AC and change the sign or operation, I get A naught plus C naught. This middle operation stays the same because, again, I'm only focusing on the NANDed situations. But now we can see that I've gotten rid of all of my NAND and NOR combinations, and I can use my basic Boolean theorems to simplify from here. So looking at what I have here, I have A naught plus B naught, that quantity ANDed with the quantity A naught plus C naught. So that has the distributive law written all over it. I can FOIL that out, and when I do, I get A naught ANDed with A naught right here. I get A naught ANDed with C naught right here, B naught ANDed with A naught here, and B naught ANDed with C naught right there. Then if I want to, this B naught ANDed with A naught, I can rearrange it so they're in alphabetical order. I can take B naught A naught and A naught B naught, because AND is a commutative operation. That's optional if you don't want to. You don't have to do that step. And then we can also look at our identity laws. We notice here we have A naught ANDed with A naught. Well, we said that if we AND something with itself, one of those inputs becomes redundant. So this A naught ANDed with A naught becomes just A naught. Then again, using our commutative law, we can rearrange the B naught ANDed with C naught and the A naught B naught C naught terms, and so that all the ones that start with an A naught are together, and they're more or less in alphabetical order. And then we can reverse the distributive law again by taking a look at these first 1, 2, 3, 4 terms. Notice they all start with an A naught, so we can factor that out. We can pull out the A naught, and if we pull the A naught out of this first term, we end up with a 1. If we pull the A naught out of the second term, we're left with just a C naught. The third term, pulling the A naught out, leaves us with a B naught, and then the fourth term, pulling out the A naught, is B naught C. However, that 1 there tells us that it doesn't matter what C naught, B naught, or B naught C come out to be, all of those are applied to an OR gate with a 1. So we know the result of that is just going to be a 1. So we have A naught ANDed with 1 plus the B naught C naught that we have left over. And then our dependent law says if we AND something with 1, nothing changes. So our A naught ANDed with 1 is just going to be A naught, which gives us our simplified expression as A naught plus B naught C naught, which is a whole lot smaller than what we started with up here. So for your individual project, you have another Boolean expression with NANDs and NORs to simplify. And what you're going to do is you're going to draw the unsimplified circuit, simplify it using DeMorgan's laws and Boolean algebra, And then you're going to draw the simplified circuit. And then I want you to derive a truth table for each circuit and to compare and verify that both of those circuits will have the same output. That'll be your individual project, and then later for your group project you're going to construct both circuits on a breadboard and verify that the output is the same for both. So please go look at the instructions for the individual project and let me know if you have questions, and then in the lab as a group you can create the circuit.